Hello everyone, welcome to Percona Live 2021. Let me share my screen. Okay, my name is Yura Sorokin. I am a software engineer at Percona, a company I truly believe you heard of. And today I am going to talk about user-defined functions, or UDFs for short, in MySQL Server. I'm telling you in advance that the difficulty of this talk is somewhere in between intermediate and advanced. I expect you to be not only a powerful MySQL user, but also a developer, because what we are going to do requires some developer skills, in particular in C++, but only on basic level. So let's start then. What is a user-defined function? First of all, a MySQL Server has already a lot of built-in functions for various purposes, beginning with string manipulations to something more advanced, like calculating hash values or encrypting data with RSA keys, for instance. But sometimes even that is not enough, and we need to create our own. And basically UDF is a way to bring your logic written in native code and run it inside the MySQL server. And this is exactly what we are going to do in our example. So in a bit rephrasing what we saw on previous slide, we need to create a user-defined function. We need to have a dynamic library or a shared object, which is how it's called on Linux, with function logic. Register this function in MySQL Server via create function as a name. After that, we can use it as any other standard built-in function, for instance, in a select statement. And after we are done, we can unregister it with drop function. Nothing special here, and we will mostly be concentrating on the item 1 from this list, how to build this shared object. As an example, we are going to implement a very simple functions which I called native reverse, and it is expected to accept exactly one string argument and return a copy of it with characters in reverse order. I am calling this oversimplified example because you don't actually need to implement this function. Spoiler alert, MySQL has already a built-in reserve which you can find following this link, but for the purposes of this talk, it will be more than enough. So I expect this function, when called with select native reverse from ABCD, to return DCBA. And I also added one corner case: when we supply a null argument to it, we also expect it to return null. So let's move forward. We will start from reading official MySQL documentation about adding user-defined functions, and the most important paragraph there is that our .so object should have 3 symbols defined. In our case, they will be named they must be named native reverse underscore init, and native reverse underscore Dnit. All of them should have external C linkage. We also notice that the same page, documentation page, says that underscore init and underscore dnit function are optional. We consider our example to be very simple, so I really don't want to bother with something unnecessary, and let's try to implement everything in the just one native reverse function. According to the same documentation, UDFs returning strings must have the following signature for the main function. I'm not going to go through all these arguments in details. I will only tell that this is a standard C way of extending something with a lot of, in my opinion, strange side effects. For instance, at line 4, you can see char star result, which is interpreted as a char buffer, where you can, in some cases, put the result. On the other hand, the same char star pointers at line 6 and 7 are used as pointers to just single character, or basically as a Boolean values. But this is C, and we have to live with this. Let's move on. So we will start our native reverse main function with checking for the number of arguments user provided. For this, we go inside args structure and find arg count members there. We just compare it with one at line 1, and if this is not the case, we are reporting error by setting 1 to error pointer, and we also return a null pointer in this case. Continue implementing the same function. Here we are extracting the value of the first argument at line 1. The same args parameter for this function has args member, which is an array of char pointers to all the arguments. In our case, we need the very first one. This is why we supply a 0 index here. We check the returned value for nullness, and if something went wrong, oh no, sorry. If we check, this is the edge case I was talking previously. So if we receive a null argument, we are supposed to return null as well. And this is what we do. We set the error to 0, indicating there was no error. At line 2, we also specifies that is now is equal to 1, which is exactly indication of null return value, and we also return null pointer here. Then if the argument we extracted is not null, we also extracted length from a different array of the same args structure at line 3. Basically, at this point, we have arg pointer and arg length, which is enough to proceed with the results. For a temporary storage, we are not going to allocate any memory manually. We are going to use stud vector of char as a buffer. You can see it's being initialized, being constructed with predefined lengths at line 1. Then at line 2, we use standard STL reverse copy algorithm to fill it with the characters in reverse order. And at line 3, we do exactly the same as we did before, setting error to 0, set is null indicator to 0 as well, and setting lengths to the length of the argument. At line 4, you see our attempt to return a pointer to internal buffer allocated in vector, but you probably already noticed that it is in red color, and it is for a reason. The main problem is here memory management. As soon as we get out of these functions, the local variable buffer will be destroyed, and along with it, its internal memory buffer will be deallocated as well. So we, in this case, we might return a pointer to a freed memory, which is definitely not good. On the other hand, we could potentially create a new buffer here, just allocate for it here and copy all the values we generated in the function logic and return it, but it will also not be a good idea because lifetime of UDFs does not at any point it does not deallocate this memory, and we will get memory leaks. So basically, this function expects us to have a buffer somewhere else and return to a pointer to it. And big problem is, where can we find that somewhere else? In our case, we had to return to original documentation and found this paragraph about init and Dnit function. And it turned out that this is exactly what we need, because the purpose of init is, one of the purposes is to allocate some memory, and purpose of Dnit to make this cleanup. You may also notice that all three these functions have one single, one common argument, init ID of type UDF init. So I guess there must be a way to put some data in it, this common structure, which would be shared between all three calls. And it turned out this is exactly the case. UDF init struct has one of the members called PTR, and what you can see, this is a quotation from real source code from Oracle. This is a free pointer for function data. Basically, it's a general purpose pointer which you can assign to anything in the init, use it in the main function, and deallocate in the init. And this is what we are going to do. But before doing this, we are going to define an additional struct called NativeReverseContext. In our case, it will have only one member called buffer, again of type vector of char. I must admit that although for this particular case it's not necessary to create a context, we could just use this stud vector of char directly. It is a common practice to do so, because in more complex functions you may need not just buffer for the return value. You may also want to share some data between the init function and main function as well. So with that said, let's move on to its implementation. Basically, at line 1, you can see that all we do is creating a context of type NativeReverseContext using the new operator, which is basically allocating it in heap, then assign ptr member from init ID structure to this context. At this point, we need to do the cast, and we return false here, indicating success. For some reason, this is a common practice in C. Actually, I know the reason, but it still looks weird to me. Let's move to the main function then. We had it before. It had changed, but these changes are not very big. So let's go through them. At line 1, you can see our attempt to extract context from the init ID arrow PTR member. Here we also need to do the cast original type. After that, we can access members of our context, in particular buffer. So at line 2, you can see how we resize it to arglength +1 and fill it with null characters. And at line 3, you can see how we use the same STL algorithm to fill this buffer with characters in reverse order. After that, again, we fill the error output variable with 0, indicating there was no errors. Fill is now with 0, again indicating that return value is not null, and specify the output length. At line 5, you can see that the color of the statement changed from red to blue. So probably right now it is safe, and indeed it is. By allocating our context on the heap in the init function, we extended lifetime of the buffer, and now it's completely okay to return a pointer to its internal memory area. For completeness, and to be honest, more importantly, to avoid memory leaks in our code, we also have to define the Dnit function. We just cast init ID arrow PTR to native reverse context star and delete it. So basically here we are doing resource deallocation with proper destructors calling. I would say this was easy, but for me it wasn't. It had a lot of unnecessary code written, and for at least for me personally, for such a trivial task, this is complete nonsense. So just to sum up, what we had to do, we had to define a new context class with shared data, which we pass through all 3 function calls. We also had to define an additional function, NativeReverseContext. Also in the documentation, it was marked as optional. And the only purpose of that function was to allocate our shared context. Also, we saw a lot of ugly casts in the main function just to access our context, and even worse, to extract values of our arguments. Also, for string arguments, it was pretty straightforward. You can believe me, for integers and doubles, this situation is much worse. The chain of ugly cast is really terrible there. And the final point is, again, although the function was originally mentioned as optional, we had to define native reverse Dnit just to delete our shared context. At this point, you may ask me, can we do better? And if there is a way, and the answer is definitely yes. And this is a main purpose of this talk. Starting from Percona server 8022, we introduce so-called C UDF wrappers. We are completely open about this. You can find original specification in our Jira ticket, and all the code in the pull request on GitHub. So what is C++ UDF wrappers? It's a set of C++ headers. In modern terminology, we can call it a header-only C++ library. You can see 5 of them on this slide. Although I am telling you, most probably you will need only the last one, marked with green, UDF wrappers HPP. All of them are located in the standard MySQL include directory in MySQL PP subdirectory and are distributed with in our packages. So how we can use it? I am calling this slide no more boilerplate. All you have to do is to implement the same native reverse function is define an auxiliary class, which I call native reverse simple at line 1. It has to have a constructor of predefined type to line 2, and it also has to include a method called calculate, again of predefined type. After that, you invoke declare string UDF macro with 2 parameters. The first one is the name of implementation class, and the second is the name under which you want to see this function to be exported in your shared object. And basically that's it. Now let's see how these constructors and calculate function are implemented. Let's start with the constructor. You can see that we have this UDF context CTX parameter, from which we call a method get number of arcs at line 1. And if this is not the case, we just throw an exception with our desired error message. And this is all we need to do for checking. Just throw an exception, it will be automatically translated in proper MySQL code with the desired error message. What about the calculate function? So we start with extracting our argument from the same CTX parameter. We call a template method getArg, to which we supply a string result as a template parameter, indicating that we expect this argument to be of string type. If it is not, a proper exception will be thrown and handled, resulting in a proper MySQL error message. And we call this function with zero parameter, again indicating that we want the value of the very first argument. After that, we check it for nullness and return default value. This is our edge case for returning null when the argument is also null. This is line 2. And the main logic is concentrated in line 3, where we return a string constructed from the reverse iterator range. And that's basically it. You don't see any memory allocations, no additional contexts defined, no ugly casts. This is all you have to do. Let's sum up what we saw so far with UDF wrappers. Again, there are some requirements to use this framework, but they are not terribly complicated. So basically all you have to do is define a class which will be in which all your functionality will be encapsulated. It has to have a constructor of a certain signature. It also has to have a method calculate, again, with a certain signature, and depending on the value, the result type of your original UDF, it is expected to return different types as well. And after all of that, you're supposed to call declare XXX UDF, where XXX is a string, real or integer. We use string in previous example, but for other return value types, we have other macros as well. And continue. We also get a benefit of much more convenient and safer access to arguments via our context. We don't have to worry about adding or allocating custom buffers or contexts. The framework will do everything for us behind the scene. And we also now allowed to use proper CPP way of reporting reporting errors by throwing exceptions, which in our case will be translated into MySQL errors with meaningful messages. And this is basically it. And I can tell you from my experience that this framework was not just an experiment. We had a request from our Kubernetes operator teams, teams that required some extensions to work with binary logs, and this is where this was tested and proved itself to be useful. I also need to tell you that not everything is perfect in this world, and there is always room for improvement, and we are thinking about it. First of all, we did this framework primarily for scalar functions, but potentially we can add support for aggregates as well. Then in 8.0, Oracle introduced a really nice component model, which would allow function after registration, and this will definitely simplify user experience dramatically. This is again what we are thinking of, and the last but not least, right now all our string arguments and return values are expected to be of type of charset Latin 1, but we have plans to support other charsets and collations as well. And at this point, I believe this is all I have, and thank you for your time. And if you have questions, please ask.